In this video, we will do the final part of section 5.1, conditions for non-singularity, by determining the rank of a matrix. Remember from before, for non-singularity, we need linear independence by rows or columns in a matrix, and we find this linear independence by elementary row operations. Elementary row operations are interchanging any two rows with one another, multiplication of a row with a multiple scalar k, or by the addition of multiples of rows to one another. Suppose we have matrix A as the following. What I do is I label the rows, row 1, row 2, and row 3. We then move on to our elementary row operations. In this case, row 3 will become row 4, row 2 will become row 5, and row 1 from the previous matrix, row 1 will become row 6. This means our new matrix will look like this. So I interchanged row 3 and row 1. Next, we want a 1 in our first entry of our first row. We already have that. So row 4 simply becomes row 7. Second, we want a 0 in the first entry of row 2. We can establish this by subtracting row 5 minus row 4. So subtracting row 4 from row 5. This will give us row 8. So what do we get? 1 minus 1 is 0. 2 minus 2 is 0. And 4 minus 3 equals 1. And we will leave row 6 as is. So row 6 becomes row 9. So now we have a 1 in the first entry of row 1 and a 0 in the second row's first entry. Now we also want a 0 in this first entry of row 3, and we can obtain that by subtracting from the row 9 3 times row 4. This will become row 12. Row 7 stays as is, it becomes row 10, and row 8 stays as is, and it becomes row 11. So row 9 minus 3 times row 7 means 3 minus 3 is 0. 6 minus 2 times 3 is 6, so 6 minus 6 is 0. And 9 minus 3 times 3 is 9 minus 9 is equal to 0. This means we now have to ask how many rows have non-zero entries. A row is classified as a non-zero row if there's at least one entry in that row which is non-zero. In this case, we have row 10 and row 11. That means there are 2 rows with non-zero entries. This means the rank of A is equal to 2. The rank is equal to the number of rows with non-zero entries. The final thing to note is that the rank of A is smaller than the number of rows. M. Our rows is denoted by M. In this case, our rank is 2 and our number of rows was 3. This means that matrix A is not non-singular. What does this mean? If we go back, we had our matrix A if we take matrix A and we write it into a system of equations, 3 times x1 plus 6 times x2 plus 9 times x3 is equal to d1. x1 plus 2x2 plus 4x3 equal to d2, and x1 plus 2x2 plus 3x3 equal to d3. There will be no solution. How do we know this? We know this because the coefficient matrix A is not non-singular. Why is A not non-singular? Because the rank of matrix A is less than the number of non-zero rows, or the rank of matrix A is less than the number of rows of A.